Okay, let's take a look at one example on using relative motion analysis, specifically translating frame formulation, to solve a multi-body problem. So I have a robot here. The robot is fixed on the base joint O. It's a two-link robot. First link OA and then second link AE is attached to point A, and I have a motor that turns both of these joints. The end effector of the robot E is where I do my manipulations. I know how each of these two links are rotating. I know the angular velocities and acceleration of both. And I know the segment length. So I want to know the velocity and acceleration of the end effector point E. Okay, this is a single state problem. So everything is at this particular instance shown. Let me write my available information in a more logical way. I know all the geometries, but I want to be more systematic, write them in a way that I can use in vector form. So RA, what do I write it? RA relative to O, this is the best, is 1I in meters. And my R of E relative to A is, I chose the square root of 2 meters as the second length because it gives me good numbers. 1I plus 1J. I also know my angular velocities in vector form. So actually it is given OA is minus 1K. So rotating clockwise, radians per second. Alpha OA is given as 0. Omega, what, AE is counterclockwise 1K radians per second. Alpha AE, this one has acceleration, and that one is also positive K, 1K radians per second square. I think that is all the information I need and are given to me, but written in a compact logical way that I can use. What I need to find, I need to find VE, VE and AE. I want to find these two relative to the base, so absolute velocities and acceleration. What can we do? Let's start with velocities. To find velocities, it is useful to note that E rotates about point A, pin joint A, given the constant length AE of that link. And A is rotating about O. So I can, if for instance A was a stationary point, I could easily find the motion of E by just considering the rotation. But the problem is A itself, the center of that rotation of relative rotation of link AE, is moving on its own. So I need to use some relative motion analysis that will help me with the solution. I know I can write VE, that's what I want to find, as VA plus V of B, oh, not B, E. E relative to A. Well, this is always true, regardless of the situation. But in this particular situation, that link AE has a constant length, and I know the motion, this relative motion looks like a pure rotation. I can write it as VA plus omega AE cross R of E relative to A. And this is the second part, is the velocity that if I had an observer sitting at point A and it's moving with A, this is what they would observe or measure as the velocity. So good, I know this, I know that. I don't know V of A, but what I can do first, to find V of A, I can look at link OA and I can note it's a pure rotation. So I can write as omega A OA cross R of A relative to O. Basically, it is the same formulation, noting that velocity of point O is 0. And this one, I know everything, so let's calculate this. This is minus K cross R of OA is only I, and I, J, K. This is my positive direction. So K cross I is J, but I have a minus, so this becomes minus J meters per second. And I substitute this here. I have V of E equals minus J plus now omega AE, which is K cross R of E relative to A, that is I plus J. And if you do the cross product, this becomes minus J. K cross I is J. Let me do this. And K cross J is minus I. So everything will simplify, equals J, and that J is cancelled. I have minus I. Or let's write it as minus 1 I meters per second. So that is the velocity of point E. It is just coming down. It doesn't have any, wait a second. No, it only goes to the right. The J components of essentially two motions of E relative to A and the motion of A itself cancel out given this configuration. So that is the velocity. The acceleration, I can do exactly the same thing. Acceleration of E is A of A plus A of E relative to A. And I'm just going to write it in one go. So acceleration of A is an acceleration of a pure rotation of A about fixed point O. So it becomes alpha OA cross R of OA, or how did I write it? A relative to O. And I know alpha is 0, so that's good. Minus omega OA square R of A relative to O. That is the first part. The second one, everything about the other link. Alpha AE cross R of E relative to A plus, or no, minus omega AE squared R of E relative to A. So this one, The problem says it's 0. So that is good. I can calculate everything. So I have minus omega squared, 1 squared, times r of O relative to A, that is I. That is the first set of a square bracket. The second one, I have K cross I plus J minus 1 squared again, I plus J. So on the first one, let's write it here. I have minus I plus, I have K cross I, that is J. K cross J is minus I minus I minus J. So let's cancel a bunch of stuff out. This J and that J cancel out. I have 3I left. And that is, no, not radians, meter per second squared. So the entire acceleration of point E is also backward. It is in the opposite of x direction. So I chose all the numbers, so things work out nicely. But as you can see, using relative motion analysis, it is easy, systematic, to find velocity and accelerations of remote points given stage-wise information about rotations of each object. So that is all I have for now.